Hello everyone, welcome to this video. In this video, we are going to talk about the basics of probability. So, we are going to start off this list of chapters, and obviously, we are going to cover each and every topic in the basic probability course. The theory related to this will also be provided, but let us begin, and I will try to list it out that what are the chapters that we are going to cover in this whole exercise. So, obviously, we are going to cover probability, and probability as a whole is basically consists of three things. So this is probability, and in this section we are going to review one of the most important fundamentals, which is set theory. Now, set theory itself is a big subject, and obviously it has a lot of sub branches, but in this section we would be trying to cover all the portions in set theory. So, set theory is obviously the study of sets. Now, we need to know what is a set, right? Okay, so a set is basically a collection of objects. So, a set is a collection of objects. Of objects. And a set can be a collection of anything. When I say objects, I do mean that a set can be a collection of anything. It can be a collection of two chairs, or in mathematical terms, it can also be a collection of two numbers, say 2 and 3. But there is something important that we need to know is that in a set, nothing repeats itself. So, what I mean by that is, let's say we have a set called A, and we can write a set in its expanded form, like we can give two curly brackets and we can list out all the elements in here if they are listable, obviously. If they are not, then we can write it in another form, which we will learn later. It's called the roster builder method. But for now, let us consider a set A, which consists of three numbers, 1, 2 and 3. Now, we need to study the properties of this set A. How do we do that? Obviously, first of all comes the terminology. So let me write it down. The terminology for the sets would be like something like this: cardinality. Cardinality. So what do we mean by cardinality? It basically means the number of elements of the set. So in this set, as you can see, there are three elements, and obviously nothing repeats itself. So just for clarification, there cannot be a set which looks like this. This is not a set. A set can only be like, if this were to be a set, it could be like only one, which is called a singleton set, where a set has only one elements, but it cannot have a repeated element. Okay, so even if it has repeated element, you can just cross it out and write the new set where you do not have the duplicate elements. So the cardinality of a set is the number of elements in the set. It is number of elements in the set. Now, how do we write that? We write that using the modulus sign, which you might have learned, which is basically, the modulus sign means that whenever you give a positive number or a negative number, it gives you always the positive result, or in complex numbers it gives you the amplitude of the complex number or the distance from the origin. But here in set theory, this modulus sign here means the cardinality or the size. So we can either write it as mod of A, or we can write in shorthand as small n of A, like that. So this basically completes our definition for cardinality, and in this case it is basically 3. Now, cardinality of a set is defined as the number of elements in this set, but what happens if the set has infinite number of elements, which is a very big concern for us. So let us say someone says us that we have a set B, and they define the set in the form 1 by n, where n is basically a natural number. This type of a notation for representing a set is called the roster method. So obviously, when we use a roster method, we make sure that a set can be represented as a formula. So the elements of the set can be represented in some pattern, like in this one. So if I actually were to list out the elements, I could, and they would look like 1 by 1, 1 by 2. Remember that the natural numbers do start from 1 and not from 0. They include all the positive integers from 1 and beyond. So positive integers and natural numbers are basically the same thing, and they are denoted by this sign, which is a double n. So if I wanted to list them out, I can list all of them out. Obviously I cannot go to infinity, but you do get the idea that yes, I know exactly which element lies where, and I do know the position of each and every element, right? So this gives us the impression that this set B has an infinite number of elements. But then again, we can also define each and every element of it. This type of a set is called a countable set. It's called a countable set. And a countable set may have a finite number of elements or even infinite number of elements, as I have just shown above. But in both cases, they can be called an countable set if they are countable. And we will learn more about how to find countability and uncountability in the analysis section, and it's not really a part of set theory right now, because this portions of set theory deals with the deeper meanings in analysis, even though in probability it's also required sometimes, using some of the basic theorems and also some of the advanced ones, but we shall do that for the later. For now, obviously this is a countable set, and if we were talking about uncountable sets, I shall give you only one example for this right now for the moment. Uncountable set is obviously the set which has infinite number of elements, because if it has finite elements, you can obviously count them by hand. So we have a set A which has infinite number of elements, and let's say the set A has all the real numbers x such that x belongs to open interval 0, 1, right? Here we can call that set A is uncountable. So which means basically it says that x is a real number here, and x belongs to 0 and 1, the open interval. So x can be any real number between this interval, right? We can show in analysis that obviously this interval 0, 1, it's not a compact interval, and thus it's an uncountable set. So just take it for granted that countable and uncountable set are a thing, and we are going to prove it later, but the applications are actually limited here, so we would not need it much. Okay, coming back. So now you know the basic idea of a set. It's a collection of elements, it's a collection of things. Now we define two basic operations, which are union and intersection. So starting with union, union of two sets can be defined using this sign, this u sign. This is called the union operator. And when you have the union operator operating over two sets, what it does is it combines the elements of both sets. So we can take an example here. Let's say A is 1, 2, 3, 5, and let's say B is 2, 3, 4, 6. Now union is A union B, and let me also write intersection side by side just so we can learn them simultaneously. The intersection sign is basically A cap B, which is the opposite of intersection. It gives you the number of common elements, or it gives you a set which has only the common elements from A and B. So A union B would be, so see, we are trying to find all the elements in A and B, right? So whatever is in A union B must be in A or B. That's the thing. So A or B or A union B, both are the same expressions actually. So this also stands for OR, and this also stands for AND. Now 1, 2, 3, 5. So obviously we are going to write this 1, 2, 3, 5. You can list out all the elements here. Now see, 2 is already written in B, 3 is already written here, 4 is a new element, we can write a 4, 6 is a new element, we can write a 6. This gives us the union of two sets. So you get the idea that A union B is basically all the elements in A and B. And obviously we cannot repeat the elements, as I have said in the earlier section that we do not repeat elements inside a set. So A union B is basically a new set consisting of all the elements which are present in A or B. Similarly, A intersection B should be the common element. So we can take one element at a time and check if it is present in both of them. So is 1 present in both of them? It's not, so we cannot write 1. Is 2 present in both of them? It is, as you can see. So 2 is a part of a intersection B. Is 3 present? Yes, it is. 3 is a part. Is 5 present? No. And we are done. So A intersection B is basically 2 and 3. Correct? Okay. So this completes our intersection and our union part, and there is one more operator which we should know about. It's the complement. So complement of a set. For this to know, we should also know about two more things. Firstly, we should know about what is a null set. A null set is basically identified by phi, and it's called an empty set, which means it has no elements. So if something has no elements, we denote it as phi. Okay, it's called a null set. And also we have another thing, u, or it can also be represented as capital omega, or it can be defined as anything. The symbol is not necessarily of primary importance here, but it's called the universal set. Okay, so it's basically the domain in which we are walking. So universal set here, it basically represents the domain or the field where you are walking in. So for example, if you are walking in the field of natural numbers, then u should be n. So when we say we are taking numbers from, let's say, capital R, which is the real numbers, so R is our universal set, and we say that the set A is basically 1 comma 2, and our universal set is the real numbers, so we are taking all the numbers from this set, this R. Then A complement, denoted by a to the power c or even a prime, both of them work. This gives us all the real numbers except 1 and 2. So the complement of a set is basically all of the universal set from which the set was actually derived. Subtract from them the actual elements in the set. So a complement would consist of all the real numbers x belongs to R, such that x is not equals to 1 and 2. So you get the idea that a and a complement together can make the whole real number, right? Because a has only 1 and 2 and a complement has everything but 1 and 2. So a and a complement's union should give us the whole real number system. This completes our basic assumptions and our basic theory of set, and in the next part we shall try to find out what are the relations between the different operators of union, intersection, and how do we apply them, and how to study Venn diagrams. Thank you.